Good morning, everyone. I'll be talking about radiation effects on commercial off-the-shelf flash memory, which is the state-of-the-art high-density non-volatile memory technology. Here's the outline. First, I'll talk about the motivation and the basic physics, why flash is vulnerable to radiation. Then I'll talk about three independent ideas that can improve the radiation tolerance of flash. And finally, I'll conclude with the outlook of future war, looking ahead for the future war. So commercial off-the-shelf electronics are increasingly used in space and defense electronics, mainly because they offer better performance, even though they have radiation vulnerability. For example, flash. Flash offers more than 1 terabytes of storage per square inch of area. However, flash has um, several vulnerability to radiation effects. So in this chart, let's look at the evolution of flash technology. So before 2014, all flash chips were built with planar 2D NAND technology. And the scaling direction for that technology was shrinking the gate length. And after 15 nanometer, there were the management, after 15 nanometer, the technology's scaling stopped, mainly because the reliability challenges were very, very severe. And then the industry switched to a newer direction, which is called 3D NAND, where number of vertical layers were grown vertically in a monolithic fashion. Now, the scaling direction has not changed. Now it is the number of vertical layers, and currently 232 layers are also available commercially and all grown in a monolithic fashion. So this is exciting, and there is a lot of innovation taking place to improve the bit density. So, however, from radiation effects point of view, most of the studies done on flash are on the 2D NAND technology. So there are several unknowns for 3D NAND, and hence it is very important to look the radiation response of 3D NAND technology before using it in the critical application. And in future, as is predicted, that it can go more than 1,000 layers, and there is not only number of layers or physical scaling, there is also a logical scaling happening where number of bits per cell are also increasing. All this poses lots of reliability challenges. In terms of radiation effects, it can broadly classified into two categories. One is single event effects, mostly caused by high energy particles like alpha particles, neutron, or heavy ions. So this is more like a transient effect where particle going through a junction, a semiconductor junction like PN junction, causes or deposits lots of charge, and it can cause lots of transient currents, and which can cause latch up or upset in a SRAM or volatile type of memories. The other important class of radiation effects is called total ionizing dose effect or TID, where high energy photons interacts with the dielectrics in the semiconductor like silicon dioxide, and they deposit charge in the dielectrics. And this is more like a cumulative effect, and hence this is very important for non-volatile memory technology because they are supposed to retain data for longer duration. So this cumulative buildup of charge in the oxide can upset the bits. In terms of radiation response of flash, so I'd like to explain this with these diagrams. So flash is a charge-based memory where information is stored in the form of electronic charge on the floating gate. Now, flash is fundamentally vulnerable to radiation, mainly because of its thicker oxides, the blocking oxide, tunnel oxide. Because of those oxides, ionizing radiation causes data corruption in flash. So let's see how or why oxides cause, creates. So let's look at it more carefully to this energy band diagram, where you can see that after ionization of the oxides, the electrons which are shown as a red circle, they leaves the oxide system because of this inbuilt field in the oxide, and the holes they remain inside or the oxide or get trapped. So as a result, the charge builds up in the oxides, or you lose stored electrons from the floating gate, and you lose the threshold voltage. So that's the reason why flash is vulnerable. Now, this is our measured data. You can see the threshold voltage. If you measure the threshold voltage of all the cells in a chip, you can get construct a distribution of threshold voltage. So this is black distribution is the one which is just after program. If you measure the threshold voltage distribution, we'll see this black. Now, with as a function of radiation dose, if you measure the distribution, we see that all the cells are losing charge, or all the cells are losing threshold voltage. And this kind of loss of threshold voltage causes massive data corruption after a certain dose. Now, let's look at why, how the technological scaling impact radiation sensitivity of flash memory. So in this cartoon, you can think about flash as a capacitor, where we have stored charge on the floating gate, and the loss of charge. Uh, you can you can you can visualize flash the gate stack of flash as a capacitance as a capacitor. So change in threshold voltage of this is related to change in charge in the storage divided by capacitance. Now, one important aspect is if we ask the question, if I have a large area flash cell and a very small area flash cell, which will be more sensitive to radiation? And it turns out that both will be equally sensitive because the the loss of charge due to radiation and the capacitance both are proportional to area, and area cancels out. So as a result, the change in threshold voltage or radiation sensitivity is proportional to oxide thickness squared. So oxide thickness is the most critical parameter, geometrical parameter that decides the radiation tolerance. Unfortunately for flash, the oxide thickness did not scale. Both the tunnel oxide and blocking oxide, there remains more than 10 nanometer across the technology node, mainly because of data retention consideration. Because flash are supposed to retain data for 10 years, those oxides are pretty thick, but in the same time, those thick oxides make flash cells more sensitive to radiation. So the bottom line here is that no matter whether it's 2D NAND or 3D NAND or whichever technology node, flash remains very sensitive to radiation. Now, there are some state-of-the-art techniques that are used for in the space SSDs or space systems. This mainly causes error correction. So whatever bit flips, you can correct the with some error correction code when you write the data refresh, retry, and redundant copies, redundancies. So, but all of this has certain limit. You cannot correct any amount of errors, and our recent research shows that even with all those techniques in a high radiation environment, your error rate will be higher, and it can fail to correct by error correction codes and all. That is more so for high radiation environment, we need to have or in high radiation environment, none of these techniques will prevent data corruption. Okay, so that's why we came up with three different ideas to improve or to increase the radiation tolerance of flash. So first is called electrostatic shielding. Now we our research is mostly experimental. We buy commercial off-the-shelf chips and we interface them with a microcontroller, and that's how we build our own system. Now, so if you look at any flash storage system, there will be two components. One is the controller, another the memory chips. So in our lab, we develop our own controller. The controller is defined by us. So we can do very basic performance like how many bit errors. We don't do error correction. And in that way, we can collect how many bits are flipped. And this is the general framework, interfacing framework. You interface the address lines, data lines, and the command pins of the chip. And that's how we interface commercial off-the-shelf memory with a microcontroller. And the interesting part with this setup is even though it is a digital setup, we can send zeros and ones, but we can still measure the analog threshold voltage because the chip internally has digital to analog converter. So even though we are sending digital command, it changes the voltage analogically inside. And that's how, for example, here, so we can change the reference voltage analog fashion, and that's how we can measure the threshold voltage distribution of chips, of all the bits inside. So that's an example how we are characterizing the memory array. Okay, so now let's talk about the radiation or electrostatic shielding idea. So what is it? So ionizing radiation not only deposits charge in the oxide, but also it creates defects. Defects and the defects locations are very important. So if you look at the oxide layer here and how the holes are moving, the holes are moving towards the floating gate because floating gate has a lot of electrons. So electric field push them there, and as a result, defects will be created more closer to the floating gate. Now, the substrate, silicon and oxide interface, that is the more critical location. If defects are created there, then it will cause a lot of noise. It will cause um, degradation in mobility and all those device performance. So the location of defects is very important. So here you can see that if a program cell is exposed to radiation, defects locations are not in a bad shape. Defect locations are far away from this interface. But if you look at an erased memory cell. So after ionization, the holes in the oxide, they will move towards the oxide silicon interface and more defects will be created along this interface. So that is the more critical interface. And as a result, um, and as a result, with more defects at that interface, this cell, the second cell, will cause a lot of reliability issues. So that is the crux of the idea that how we can prevent the defect location in the oxide silicon interface is we have to just program it. Right? Before we deploy an SSD to a space, we need to program it with some random data so that this interface is protected. So that's we're calling as electrostatic shielding. Okay, because if you means after radiation exposure, if you erase the memory and write a new set of data, the data written on those program cell or group 1 cells will be more secure because electrons are stored in the floating gate or near the floating gate. But if you look at the group 2 cells, which were in the erase state, which is a typical condition, then you can see the electrons are stored in the oxide silicon interface because of the trap states, and they will lose out charge very soon. And that will be less reliable. So that's the key idea of electrostatic shielding. Okay, so programming cells minimizes the permanent defect creation. So this is our experimental evaluation. So or the experimental evaluation of electrostatic shielding. So we first expose the memory chip. Some blocks are in the program state, which are calling as group 1 cell or green cells, and some cells are in the erase state, which are in the group 2 cells. And now after radiation, we erased the entire memory and wrote a new set of data, and we found that group 2 cells are losing data quickly than group 1 cell. So that's the idea of electrostatic shielding that no matter what, when you deploy some chips in the space, you should program it with a higher programming voltage. So here in this chart, we show that what programming voltage you should do, and it turns out that the highest or close to highest programming state is the better for protecting the oxides. Okay, let's go to the second idea, which is the defect engineering. Which is the defect engineering or how, which is defect engineering. It's very interesting that we find that by intentionally making the oxide defective, we can make it more radiation tolerant. We can make the cell more radiation tolerant. So here is the conceptual picture that if you look at the radiation-induced charge loss, we found there is a significant cell-to-cell variability, even though all the cells undergo the same amount of radiation. So here, let's see the red cells. So they are shifted more after radiation, and the blue cells, they are shifting less. So we are calling it radiation tolerant cells. Now, this is the measured data from millions of cells. You can see that after after radiation, the change in VT, which is the y-axis, is varying from -1 volt to 0 volt. So there are certain cells which merely lost any voltage, but there are many cells which lost more than a volt after a 50 kilorad of radiation. Okay, and these cells are repeatable. It's not like in one run. Uh, it's not because the gamma radiation is quite uniform to the chip. So all the cells experiences the same TID. And if we repeat this experiment, the TID tolerant cells remain TID tolerant and TID prone cells remain TID prone. So that means it is um, it is something to do with the properties of the cell. Okay, and this is the dose by dose slope. You can see that the blue cells, which are the radiation tolerant cell, they have a very flatter slope compared to the red cell. So we dived into it that what is the and so this is our hypothesis. This is our hypothesis. That's what's going on. So a trap-free cell, which is an ideal flash memory cells, is found to be more radiation prone because a trap-free cell will have higher oxide field, and oxide fields are very critical to separate radiation-induced electrons and holes. Right. So after ionization, holes will be trapped in the oxide in a trap-free cell. But if you look at a interface trap-dominated cell, right? So if there is a lot of interface traps, then electrons will be stored in the interface during programming, and as a result, electric field in the oxides will be much smaller for a trappy cell like this. Now, less electric field will help in radiation because after ionization of the blocking oxide, for example, here electrons and holes will recombine and you will not see a net charge develop in the oxides. And as a result, this interface trap dominated cell will be more radiation tolerant. So that's the idea. And this is the mathematical way of looking at it. And that's the basic idea that we, but this also offers a trade-off because a trappy cell will have lesser retention, long-term data retention. Maybe it will not be able to retain data for 1 year, but but if in 1 year there is a high radiation dose, so for a high radiation dose or for the dose rate, if the dose rate is very high, then this idea will be better, or this is the way this will have more radiation tolerance. So there is a trade-off between long-term data retention as well as radiation tolerance. Okay, so this brings to the last part of my talk, which is the watermark. Now, the main reason why flash is vulnerable to radiation is its stored charge, is the charge-based memory. Now, if you can store information without involving any charge, then it will be much more tolerant to radiation. That's the key idea. And the way we're thinking about it is okay, we have a flash cell with a transistor, and based on the oxide property, if we can store information, that will be more radiation tolerant. So let's look at here. So this is a trap free and ideal flash cell. We call it logic one. And if we somehow introduce defects in the oxide, which is called soft breakdown of the oxide, then it is a bad oxide, bad quality oxide, and that cell is called logic zero. So this soft breakdown, if we use the soft breakdown in our favor, or if we can selectively choose certain cells and cause soft breakdown in their oxide, then we can imprint another set of data without involving any charge. So this is more like an anti-fuse type of memory or one-time programmable memory where the oxide is broken and we are that's how we are. So this will be a one-time programmable memory analog. And the way we do it is as follows. So we have, suppose we want to watermark, say 2019, and here, and this is a digital equivalent. So all we need to do is erase the memory, write the data, again erase the memory, write the data. If you do it repeated times, 1,000 number of times, then the cells which are changing their state in this process, electrons are going in and out of the oxide, they will undergo oxide breakdown. So they will eventually become bad. And the cells which remains always in the erased state, they will their oxides will be good and they will remain in a good state. So this is how we can imprint watermark, and that's how we can write another set of information without involving charge. Now we found that this is tolerant to radiation. So this is our evaluation result, experimental evaluation result. So this is a good memory cell which has no defects in the oxides, and after TID or total ionizing dose effects, there will be some defects will be introduced in the oxides. However, if you look at a bad cell which has several oxide defects, even after TID, that remains bad, right? So this logic one and logic zero, we can still distinguish after irradiation. So that's our uh, collection data, collected data. So we wrote on the same chip. One is charge-based data written on one certain blocks, and certain other blocks we wrote watermark. And we found that for very high dose response, watermark performs better, or the rate at which the error rates or bit error is happening in the watermark is much more. Of course, watermark starts with a higher bit error rate because we did not because it is hard to exactly quantify or exactly identify who is good and who is bad. That's why it starts with a higher bit error rate. But for charge-based data, you can see the bit error rate is exponential. After certain dose, we cannot correct the data anymore. It becomes uncontrollable. Okay, so with that, I would like to conclude and want to talk about the future direction in this field. So I talked mostly about NAND array, where the or NAND bits where data is stored. But if you look at a NAND flash chip, there's lots of peripheral circuits. Peripheral circuits can be decoder, charge pump, because flash memory involves 15-20 volts. And from the external voltage source, we supply only 3.3 volt. So internally, the voltage is amplified, and that's why the charge pump circuits are very important. What turns out that after radiation, before the array fails, charge pump fails, or charge pump becomes more and more weaker. And as a result, the timing, if you look at the timing, how much time it takes to say erase the memory, that becomes significantly higher after radiation. Or so, and once the timing becomes very, very high, then the chip becomes non-functional. So the real cause of death of a flash chip is not the memory array, is the charge pump and other peripheral circuit which stops functioning. And as a result, the chip becomes functional. So that is the more critical issues going forward if you want to use flash for a very high radiation environment. Okay, so and that requires more research or different process how these chips are fabricated. So with that, I'd like to conclude. So first, we have talked about the flash as a fundamental vulnerability to radiation, one fundamental reliability issue.